everybody, and welcome to another exciting Astronomy on Tap. It's very good to have you all with us in 2021. We're starting our program this year online, as we've been doing for the past few months. This month we have two very exciting talks, both sort of on the topic of radio stars. Firstly, our own sun, which is radio star 2, and then secondly about other stars and the planets around them. So for those of you who don't know Astronomy on Tap, if this is your first time joining us, welcome. Astronomy on Tap has been going for a number of years now, since 2013. It started in New York City, and since then spread across the US and then throughout the rest of the world. The first one here in Europe was Astronomy on Tap Leiden, and we've been going since March 2017. And we usually meet the last Monday of every month, usually in Leiden here at a local bar. But the past few months we've been meeting online, and it's really great to have you with us tonight. Do check us out on social media. If you're on YouTube, you've obviously found our YouTube channel. We have a website as well, but check us out on Facebook, on Twitter, and Instagram. And you can always email us for information. But yeah, if you're on any of these social media sites, just give us a shout out tonight. We'd love to say hi. On the YouTube channel, welcome to all of you. Do give us a shout, say hello, tell us where you're from. It's really great that we're able to meet with so many people, even across the world these days. So that's one real benefit of doing this online. And during the two talks, if you have any questions, you can leave them in the YouTube chat. Just write them down whenever you think of them. That helps to get things going. And then one of our team will ask the questions to the speaker in our channel after their talk, and they can hopefully answer your questions. So yeah, we're looking forward to hearing from you. It's great to have you along. The first thing we do is give a little bit of astronomy news. So there's been some exciting things over the last few months, the last 2 months since we've been online. And the first thing was something quite recent. It's really quite exciting, and it's kind of similar to the work I do. There's a new record for the most distant quasar found. So quasars are when supermassive black holes at the centers of galaxies consume material, and then, in fact, they actually give off a lot of light. They give off a lot of energy. In fact, thousands of times all the light from all the stars combined in our galaxy. These objects can shine as bright as that. So this is a record. This one is found now 13 billion light years from the Earth. And this was when the universe was just 670 million years old. So it was a really young object. And surprisingly, there's objects like this in the early universe where there are black holes that are a billion times the mass of our sun. So there's lots of open questions here. How did these black holes get so big so early on in the universe? So this is really exciting news. The other thing, and there was actually quite a lot of information that came from this, the telescope Gaia that really accurately measures the positions of a whole lot of stars, recently released a new set of data, the data release 3. So a lot of astronomers were very keen to get on board with this and start working with this new data. So they had a lot of results come out. And one of the really cool things is that, again, using quasars, so these are really, instead of just the stars that Gaia measures, it also measures the positions of these quasars that are very, very far away. And because they're so far away, they're essentially at rest. So we can compare our movement to that of these quasars very, very far away. And in the same way that if you're standing in rain, you just see the rain coming down at you. But if you're running through the rain, it seems as if the rain is coming from a different direction. Using these very tiny shifts of the positions of quasars in different parts of the sky. The weird thing is they're actually able to measure very, very precisely how the Earth, well, not the Earth, how the Gaia satellite is actually moving in space. And it's moving around the sun, and the sun itself is moving around the center of the solar system. It's actually not quite the sun itself. The sun is moving around the center of the solar system, the barycenter, and that is moving around the center of our galaxy. Our galaxy is also moving through the universe itself, but it's this motion of the sun around the galaxy, so our solar system around the galaxy, that they were able to measure for the first time using optical data. So that's a really cool result. And this motion is about 1,000 times less than the motion of the sun itself around the solar barycenter. It's a very, very small effect. And it's only with really good quality data that they're able to measure this. So it's really exciting. So that's just two really cool things that have come out in the news recently. But on to tonight's program. Tonight, as I said, we've got two talks. But just the structure will be our first talk by Ciara Maguire, talking about the radio sun. Then we'll have our usual quiz. There'll be a link in the YouTube channel to a Google form that you can fill out and follow the quiz. Then we'll have a short break for the order of 10 minutes or so before we come back with the second talk, Joe Callingham, about life around a radio star. And surprise, surprise, Joe also came with his own quiz. If that works, you'll have to pay attention. Then we go on to our quiz answers and announce our winners. So play along, you might get something. And then we'll just wrap up at the end. But without taking too much more time, our first speaker is Ciara Maguire. She's a solar physicist and also a radio telescope operator. She's currently doing her PhD at the Trinity College in Dublin and also the Dublin Institute for Advanced Studies. Her daily work is to analyze solar observations from different instruments, both in space and on the Earth. And when she's not doing that, she likes to be hiking in the Irish countryside, which you can see from this picture is absolutely beautiful. She's also quite partial to a pint. So for her talk tonight, Ciara is going to talk about our sun and all the different kinds of light that it produces, how we detect it with different telescopes, and how all of this we put together to better understand the solar activity and how it affects us here on Earth. So Ciara, over to you.
Great. So thank you very much, Wendy. Hopefully you can all see me and hear me all right. So as Wendy mentioned, my name is Ciara Maguire and I am a PhD student working in Dublin in Ireland. And I work with two institutes, so it's Trinity College Dublin and the Dublin Institute for Advanced Studies. And this evening, I'm going to talk to you about some of the research that I do with my research group there and how we use images of the sun that are either taken from instruments maybe on the ground or some instruments that are in space on telescopes, and how we're using them to understand and unravel some of the mysteries behind our sun and its activity. And I'm going to fill you in a little bit at the end about why this research is important and why it kind of has effects for our society as we know it. So hopefully you'll have lots of nice questions for me at the end. So first, we'll get stuck into it. Hopefully it's an object that you're familiar with. I study the sun. And if I was to ask you to think about the sun and you might maybe to draw a picture of it, you might draw something similar to what you can see on your screen here. So just a giant orb in the sky, maybe orange or yellow in color, with not much else going on. And that is exactly what we see if we were to look at the sun with the naked eye. Something I don't recommend that you do, please don't go look at the sun, but if you were to, this is what you'd kind of see. And it kind of seems quite boring initially, but if you do look closer, you can actually see that there is a bit of detail, that hopefully you can see my mouse here, that there's actually kind of marks on the sun's surface. And this is something called a solar sunspot. And you see that they kind of revolve as the sun is revolving towards us. So they're on the surface of the sun there. And these are kind of the first clues that there's something more going on, because these sunspots, they come and they go and they grow and they change in shape. So this is kind of a clue that maybe there's more going on than meets the eye. But what we have to bear in mind is looking at this image or looking at this movie of what we see with, if we were to, our own telescopes, our own eyes, it's just one part of the picture. the sun can produce many different types of light. And unfortunately, we can only see one type. So we need help to see the other types of light. And these types of light, you're probably familiar with some of them, but maybe didn't realize that they're in that category. So things like X-rays is a type of light, extreme ultraviolet, infrared waves, gamma rays, radio waves. These are all different types of light that are part of a spectrum, something that we call the electromagnetic spectrum. And they're kind of categorized based on how much energy they have. So we have high energy, mid energy, and then low energy light waves. And we divide them up and kind of categorize them this way. And we measure them as kind of energy. We use something called frequency. That's how we distinguish at a high frequency, which means a low energy radio wave, and vice versa. So this kind of helps us categorize these different types of light. But we can't see them ourselves, so we need a little bit of help. And that's where telescopes come in. Either ones on the ground that can help us look at light that comes all the way through our atmosphere, or ones in space, say on a satellite, for light that can't get through our atmosphere. So if we were to look at some of the telescopes that look at the different types of light, we'd see a very different picture. So the sun, on the exact same day, the exact same time, if we were to look at, say, ultraviolet light, we'd see a completely different picture going on. So you can see, this is, again, it's the exact same time, but there's a lot more detail. We're looking at a different energy. We're looking at different activity on the sun, even though it's the exact same time. And you can see, if you look closer, you'll see kind of dark patches on the sun's surface interwoven with these really bright, active, dynamic regions. And they kind of keep changing, and we see these looping structures, which are in fact the sun's magnetic field. And you can see it's constantly changing and moving in shape. And these are the regions that we're really interested in. You might be able to tell that, in fact, they line up exactly with where we saw those sunspots. So this is the regions we're interested in as scientists, because it's at these loops and at these active regions that we see that loop become so twisted and kind of contorted that the two sides meet. And when they meet, a big explosion happens, something that we call a solar flare or a solar storm. And in this process, a huge amount of radiation and heat and all different types of light are released as that reconnection occurs. And this is something as scientists that we want to study. We want to study every single step of that process, from the twisting to the release to the heat being produced and all the different types of light, plus the really pretty cool images to look at. So I'm going to show you one of them in action and how we look at it as scientists. So but before I start a movie, it's going to show you pictures of an event, or a movie of an event. And we're going to start really zoomed out from the sun. So we can look at the atmosphere of the sun. And we do that, in fact, by blocking out the really intense light of the sun. Just as if you were to block out, say, the light in your room, you'd be able to see maybe flecks of dust around your bulb. We do that by, it's essentially the same of looking at the sun's atmosphere. And then we're going to zoom right into the sun's surface, see one of these flares occur, see where maybe some different types of light are coming from, like X-rays, and then zoom out again and see what happens. So I'll get that video going. And just to remind you that the different filters here and colors represent different telescopes and what we're looking at. So we're looking at the sun's atmosphere, material being expelled outwards, zoom right in, looking at extreme ultraviolet. That red there is actually X-rays, so we can see where they're coming from. We watch the solar flare, and then boom, it's followed by this huge explosion and material being expelled outwards in what we call a coronal mass ejection. And you'll notice there's actually flickering at the very end of that video. And that's actually particles from the sun hitting the telescope itself, hitting the CCDs. So they're quite nice and quite cool to watch these videos. So we can get a really good overview of what is happening. So we can zoom right in to the surface, see where those X-rays are coming from again, where that red is. And then we can look at the solar flare occur, and then watch as the evolution of that material being expelled outwards. So instruments like this give us a really good insight into what is happening with the solar flare. But we need to look at all different types of light, and sometimes we need to make different measurements. And I mentioned there's an entire spectrum of light that we can look at. And myself and my group in Dublin, we look at radio waves from the sun. So we need a radio telescope to do that. And luckily we have one. So there is actually an entire network of radio telescopes in Europe, something called the Low Frequency Array, or called LOFAR for short. And this is a network of radio telescopes which starts in the Netherlands. It started in the Netherlands and is now connected to lots of international radio telescopes that are dotted throughout Europe. And Ireland joined this network in 2017 when we built a radio telescope right in the middle of Ireland in a small town called Birr. And this is what it looks like. So it's not really what you'd imagine when you think of a telescope. There's no mirrors, there's no fancy lenses. It's the size of a football field, and it's made up of these structures here, which are different types of antennae, which pick up the radio waves. So you have one here in the corner, which is kind of a pyramid shape. These wires here, they detect our radio light. And there's actually, under this black tarpaulin here, we have a different type of antennae, which is this kind of triangular metal blade that you can see in the kind of polystyrene structure there. And that is a part of the telescope that detects a different type of radio wave at a different energy, at a different frequency. So we can use this radio telescope to detect radio waves from the sun. And hopefully those radio waves will tell us more about what's going on. So in the context of all the videos that you saw earlier and those huge explosions, where does our radio telescope come in, and how does it help us and help us as scientists? Well, in the solar flares that you saw, right at the, can maybe say if one was to occur on the edge of the sun there, in the process of that big explosion, that reconnection happening, radio waves are produced due to the physical processes that go on there. We know that. And radio waves are then emitted, and they travel all the way to Earth and can be detected by our telescope. And we can measure them. And the measurement that comes out of our telescope is something like this. So it looks horrific. It's not a pretty picture. There's no nice big explosion happening. It looks just a bit mad, and it looks a bit like noise. But it is actually, trust me, it is actually really useful for solar physics and for solar physicists. So what it is, it's measuring frequency, so the frequency of the radio wave, or the energy of the radio wave over time. And the colors here are important. So you have blue meaning nothing, and then red meaning more of something. So at a particular time, you can see like a red streak. So that means a lot of radio waves were emitted at that time. So from the middle of Ireland, we can tell that something has happened at the surface of the sun to cause one of these radio waves to be emitted and for us to pick it up. So it gives us clues as to the physics that's going on. And we wouldn't get this just from the pretty picture alone that you see on the left. So we need these we need to look at radio waves to get the full picture. And as solar physicists, we study these blobs and shapes and how long they last for, and where they are and how often they happen, in order to figure out more about the physics that's going on at the surface of the sun. So we can kind of unravel some of its secrets. And that's what we do. We study where these radio bursts are. So those mad shapes are called radio bursts in the context of the sun. So this is just some research that was published in a paper in Nature Communications a few years ago. So there's an event occurred on the sun on the edge, and we analyzed images that were taken in one type of light, in extreme ultraviolet, and then saw these contours here represent where the different radio bursts are coming from. So you wouldn't get to see that by just looking at one form of light. We must look at all different forms of light to understand the physics of what's going on. And why is this important? Question I ask myself a lot, particularly on those tough days when I don't know what I'm doing with the research. It's really important that we study the physics of the sun, because it is our closest star, because it has huge impacts for us here on Earth. And the whole area of solar physics ties in really well and is really dependent on a whole area called space weather. So just as we have weather predictions and meteorologists to determine when there's going to be storms, we have space weather predictors who want to predict basically solar activity, because it has huge effects. So if one of those huge explosions that I showed you earlier was to be on, say, the side of the sun that's facing the Earth, all those highly energetic particles, all that radiation would come hurtling towards us. And that would have huge effects for things, say, like our satellites, they're just made of wires, so it would cause them to short circuit. Also, the radiation would have impacts for those, say, on the International Space Station, because it's just harmful for humans, and also those in the aviation industry. But it can also affect things that are on the ground. It can give us some nice effects like the Northern Lights, but it can have detrimental effects for our electricity grids, our communications, because they're all made of wires and circuits, and lots of particles affecting that and lots of radiation can cause huge damage. So understanding all the physics behind our solar flares and studying every step of it means that if we see step 1 and 2, we know that step 10 and 11 will follow, and we can take the necessary precautions so that none of our satellites or communications are disrupted because of solar activity. So that means that solar physicists who are like all around the world and with my group in Dublin, we're studying events like this and these huge explosions and trying to understand the physics behind mechanisms like this to help us hopefully protect some of the infrastructure that we have here on Earth. And plus it means I get to play with some cool images of the sun. So thank you very much for listening, everyone. I'll leave that there.
Excellent.
Welcome. Any
Thank
questions?
you very much, Ciara, for your really, really nice and interesting talk. And I'm sure, like, I really enjoyed it, and I hope our audience also enjoyed this really interesting journey of learning more about our own sun. So we already have a few questions in the chat. So the first one is from Apache 4381. And this person said that why the sun has so many activity around the middle region and not at the poles? Thank you.
It's a really good question. It has to do with the sun's magnetic field. So it does change over time. So sometimes there is more activity over a few years and then there's less, but that has to do with where the magnetic fields emerge. So there's a lot more material around kind of the equator. So less things are likely to happen up in the poles. Also, there's a bit of an element of that we don't see it, because we can only get one view of the sun. So there's not too much studies about what's happening at the poles, but it has to do with how things are moving on the sun's surface. It's a plasma, so the magnetic fields are constantly changing. Whereas say on Earth, we just have kind of a stationary magnetic field, like in a magnet, like a bar magnet.
Great. I hope that answers the question.
I hope so.
For Apache 4381. And then we have one more question from Fred Sundarman, and that's is the chart of frequency versus time, in the chart of frequency versus time, does the frequency refer to the wavelength detected?
Yes, yeah, so frequency and wavelength are very connected. So high frequency means like a longer wavelength. So the different types of light, they're kind of categorized using wavelength. But then for some reason, when it comes to frequency light, we use frequency. So hertz is like a unit to describe it. But it's the same concept. So it's a good physics question.
Thank you. And then there is one more question about the same plot, actually, that in the frequency versus time plot, there are distinct horizontal constant frequency lines. And are those commercial frequencies?
That is a really good question. Yes, that's something we call interference. And that band, so you can see it's a cross, so it's in a constant frequency. So it can be due to some radio waves coming from the nearby town. Sometimes if there's electrical fences around the area, you can pick them up. If there's CCTV close by. So we've been really careful with our telescope in Ireland to kind of avoid all those things, because as we saw, they come up and they block what we're trying to look at. So we try and minimize them, because otherwise it takes away from the science that we're trying to look at.
Mm-hmm. Thank you. There is no more questions for now, but there are a lot of applause from the audience that it was a great talk. They also really liked it.
Thank you.
And yeah, so maybe if there is more question, you can check the YouTube chat that we already have, and maybe you can answer later if you see something that's coming to you. And with that, thank you once again for your really excellent talk. And now we move on to the games, and Stella will present the games now.
Hello, everyone, and welcome to the games. As always, you can find the link to the games in this slide in the bottom, or there should be the link also given in the chat already, or in a few moments, it will be there. But while you go and fill in your email and team name, etc., I just wanted to mention that last time in November, we had some feedback for the games. I really thank the people who took the time to give us some feedback. And also this time we have added a few questions in the end of the games forum to give you an opportunity to give us feedback if you'd like. For example, you can share what you liked about the games today, what is your favorite question, or just generally anything you would like us to keep in mind when we make the games in the future. I also wanted to mention that as we did in November, I won't repeat the questions another time, but you can yourself go through the stream by just dragging the red line in the bottom of YouTube and just check the questions if you so wish during the pause that is right after the games. And with that in mind, I will start slowly going to explain what the game is about. So the first game is like we had in November, it's fill in the blanks. So we will show you multiple different pictures or images, and you have to fill in which answer goes with which image. And we only have each of them matching one, so there's no trick here with every single answer being the same one. Right, so let's start. First question. Where are these radio telescopes located? The answer options are below, and you will also see them in the Google Forms in a grid-like manner. So go ahead and try to guess them based on the pictures. All right, moving on to number 2. With these telescopes, you could theoretically be able to read a newspaper in blank, standing in blank. First one is the Event Horizon Telescope, shown on the left-hand side, and second is the Atacama Large Millimeter Array, shown on the right-hand side. And the options are reading a newspaper in New York while standing in Los Angeles, and answer B, reading a newspaper in New York while standing in Berlin. Okay, let's move on to number 3. The longest baseline for these telescopes is, and the answers are 16 kilometers, 8 kilometers, 36 kilometers, and 8.6 kilometers. And the baseline means it's basically the largest, the distance between the furthest of these antennas in the array. So the furthest distance between the antennas. All right, moving on. Number 4. What wavelength is this image of our Milky Way taken in? Yeah, there's 4 images, and the answers are either optical, radio, X-ray, or infrared. All right, moving on. These radio discoveries were made in in the bottom, there are some years, and in the middle, you see the different discoveries that were made with radio telescopes. So the first pulsar discovery, first exoplanet discovery, the direct imaging of a black hole, and the detection of neutral hydrogen by the 21 centimeter line. Right, and this actually concludes our first game. So moving on to the second one. Right, I think you should be still able to go back and forth between the pages later. So if you're unsure about anything in the first one, just don't submit it immediately and see again what your answers were currently. So the second game, it's find the host. Can you find the counterpart of these radio images? First, I will explain a little what this game entails. First of all, we have, in this game, we will use the Milky Way's diameter as a distance measure, just so it's a bit easier to conceptualize. And I will show you now an example of what we'll be doing. In this image, you see Cygnus A, an elliptical galaxy in visible light here in the center. And if you look at the same vicinity of Cygnus A in radio, you see something completely different. You see these huge jets emerging from the center of the galaxy. And this is due to the galaxy hosting a supermassive black hole and an accretion disk around this black hole, which is basically just matter orbiting very close around the black hole. And now, when you combine these two images, both the visible light image and the radio image, we see this. So we actually see where the jets originate from. The extent of this is pretty huge. It's 3.5 Milky Way sizes. And the extent of these jets usually depends on the amount of time that has passed since they emerged. So obviously they grow and move away from the center as they grow. And the structure of these jets is mostly determined by the surrounding environment that they're in. And so what the game entails is that we show you a radio image of these kinds of jets, and we ask you to guess where they originate from. So what is their host? Okay, so let's see how it goes. First one, it's Hercules A, and the entire extent of this is 11 times the Milky Way diameter. And the options for the host are shown here. A, merging galaxies, B, group of galaxies, or C, supergiant elliptical galaxy. All right, moving on to the second one. Here we have Centaurus A, and this one is now 10 Milky Way diameters across. And the options are A, supergiant elliptical galaxy, B, group of galaxies, or C, lenticular galaxy. Okay, moving on again. Here we have Fornax A, and this one is 7 Milky Way diameters across. And the options are supergiant elliptical galaxy, merging galaxies, or lenticular galaxy. Number 4. yeah, I'm not going to start pronouncing that name. So here we have some jets that are 4 times the Milky Way diameter across. And the options are A, a spiral galaxy, B, group of galaxies, or C, supergiant elliptical galaxy. Five. Not going to pronounce that either. This one is really large. It's 50 times Milky Way diameter across. And the answers for this, not the answers, the options, are A, group of galaxies, B, merging galaxies, and C, supergiant elliptical galaxy. And finally, this one is a little bit smaller, just 1.5 Milky Ways across. And the options for this are A, merging galaxy, B, group of galaxies, or C, supergiant elliptical galaxy. Okay, and finally, as always, we have a tiebreaker. The most powerful radio telescope in a few years will be the Square Kilometer Array. Out of how many stations will this telescope consist? Right, so with that, we conclude the games. And as I said, you can go back and check further if you have another thing you needed to check for the questions. But otherwise, we'll be back soon with the answers.
Okay, and we are back. So I hope you enjoyed the game. I noticed one of the questions in the chat was about what else you can use LOFAR for, and you'll have seen some of those images in the second game actually came from LOFAR, so you can use it to study these giant jets, which is also cool. But in our next talk, Joe is also going to show you some other things that LOFAR and other radio telescopes can do. So our next speaker is Joe Callingham. He's an astrophysicist from Australia. He works here in Leiden at the observatory, but also at Astronomy, which is the Netherlands Institute for Radio Astronomy. And he studies everything from radio stars and exoplanets to the evolution of galaxies. And apart from doing radio astronomy, he also likes surfing, running, reading, and a schooner of beer. I'm not sure if I said that in the Australian way. I had to look up the word. And I'm assuming you mean an Australian schooner, not a Canadian schooner of beer, which is apparently at least twice the size.
Yes, I would prefer whatever floats your boat, Wendy.
2 pints and wine.
A schooner of a boat of beer, is also another option.
That is the first thing I thought when I saw that. But a fun fact about Joe is that he thinks that modern symposia are far too dry, and we should just go back to the classical Greek way of doing things. Maybe you want to say a bit more about that. But tonight, Joe is going to be talking about how astronomers can identify, that astronomers over the last few years have learned to identify planets really easily around stars. But the open question is still whether they can host life or not. And that's one of the big questions everybody's asking. But Joe's going to talk about how radio astronomy can actually tell us something about life possibly on exoplanets. So over to you, Joe.
Thanks, Wendy. Yes, bold area. You sold me very hard. I'm going to solve all the problems about life. All right, let me just share my screen and make sure this works. Hello everyone. My name is Joe Callingham. As Wendy mentioned, I'm based at Leiden in Astronomy. As you probably could tell from my accent, I'm not Dutch. I'm Australian, but I've been living in the Netherlands now for nearly 4 years. and I've been enjoying myself here immensely. And what I'm going to do and talk to you about today is about some of the research I've done here in the Netherlands about trying to find planets around other stars and whether such planets could exist life. And Ciara's talk just beforehand really set this problem up really well for me with the idea that stars can have these explosive eruptions and all kinds of interesting stuff going on in their surfaces that make life, like we have on Earth, a difficult thing to exist elsewhere. And we might discuss how we can try and understand that and try and find Earth 2.0 or something equivalent, or 2.0, depending on the way you want to pronounce this. So, or pronounce. I hope you got your drinks charged. So Wendy kind of gave a precursor. I'm going to have a little quiz in the middle, but there's a delay between the YouTube stream and what I'm talking about here. It's essentially a 25-second delay. So I'll explain more on the later, but just keep that in mind when we go to answering the questions. And so this questions will actually be over Kahoot. I'll give again more details later, but if you just want to put kahoot.it in any web browser you have on your phone, your tablet, your computer, that's where the quiz will be. It'll be very short, but it's just to keep your attention and not become very bored. Unfortunately, I'd love to do this in person. These are really fun talks, Astronomy on Tap, when they're in a bar and you can kind of gauge the audience and you can play off each other. Obviously, I can't do that. I'm staring at a computer screen, but hopefully out there you'll have fun with this. And just let me know, or Wendy know in the chat, if I'm speaking too quickly or any of those other issues that I commonly fall into as I give talks. So let's get underway. You might have seen pictures like this. Whenever you hear about an astronomy research, you have these beautiful pictures of a star in the background and a planet in the foreground, or maybe one like this, or one like this, or one like this. It's almost science fiction, they're beautiful images. Every single one of them, right, are absolutely fascinating, but these are all kind of built on what scientists and astronomers discover. But at the end of the day, we're incredibly lucky to have our artistic friends out there that can really visualize what we're discovering. And so just as I mentioned in my opening slide, a big effort in astronomy right now is some of the most interesting questions I think you can ask as a human is there life out there? Are there other Earths out there? Is it possible to live on those other locations? These are fascinating questions that deserve to have answers to them. And we're super lucky, incredibly privileged as a person to live in this time period where we're starting to crack this nut, where our telescopes are getting sophisticated enough to begin to answer these questions. We've got a long way to go. This is early days, but for the next 20 years, I can guarantee you will find an Earth-like analog in the next decade or two, which is like phenomenal considering literally 20 years ago is when we found the first planet around another star. We all thought they existed, but now we have proof of them. But the point I'm trying to make with this slide is we're trying to find Earth 2.0, the classic idea of like water on the surface and all this kind of just direct analog stuff. That obviously finding life is a lot more complex, but if we just keep it to finding Earth 2.0, we know life exists on Earth, so maybe life exists somewhere else out there. These are the type of planets we're looking for. Unfortunately, most of the time, I don't look at pictures like this. I wish my job was to stare into nice, pretty pictures. And we have to thank these two men for that unveiling of the first exoplanet, and they won the Nobel Prize in 2019. This is Didier Queloz and Michael Meyer. I'm probably butchering their names. They're both Swiss, and they made the first discovery. I'll show you the first picture. Oh, well, picture in a quotation mark sense. If you can see me online, I'm using rabbit ears on my fingers. This is the first picture of the first exoplanet. So what you're seeing here is a planet around a star called 51 Pegasi. And on the left here is a complicated diagram that's telling you about the Doppler shift of the star. So this star is so far away, even with our biggest telescopes, if we turn them on, we can't ever be able to resolve them. They're just too far away. This is like the equivalent of seeing headlights in the distance on very far away, kilometers away on a night that's quite clear. You will never be able to see the two headlights if it's too far away. You only can see one headlight. You can't resolve the car's headlights. And this is kind of similar. This star's so far away, even with our biggest telescopes, we can never be able to separate the star and planet. The star just dominates, and that's all we see. But we're very lucky because gravity obviously exists in our universe. And what happens is the star goes around the as the planet, goes around the star, it causes wobble in the starlight. And this is what this sinusoid is. It's just what the star wobbling. It's coming towards us. That's what the positive numbers mean on the x-axis, and then it's going away from us. That's the negative numbers. So to visualize this, this is all just the Doppler shift. So hopefully you don't have your headphones too loud. Hopefully you don't have your headphones too loud. No, I was meant to probably give a better precursor to that. What I'm showing here is that this curve here is the Doppler shift. As a star comes towards you, the light is squished a little, so it looks a little bluer. And when it goes further away, it lengthens out, becomes red. And you've all heard this effect before. When an ambulance goes by, a police car goes by, you hear it higher pitch, and then it goes lower pitch. And that's what I was trying to show with this video here. As the train comes closer, it goes a low pitch to high pitch, and then low pitch. And so to visualize this,
Joe, sorry.
Yes. Yeah. Could you hear that or not?
Was there sound on that video?
Oh, there was sound on that video.
You might need to make the sound. You didn't share it.
Oh, that's okay. Don't worry then. We'll move on from that sound issue. Anyway, at the end of the day, the thing I was trying to communicate to you is the ambulance sound. You hear it kind of high pitch to start, and then it goes low pitch to finish. And this is one way to visualize what I was explaining before. As the planet goes around the star, on the bottom here, you have this spectrum, how the star emits light at different frequencies, and you can kind of see the spectrum moves back and forth as the planet goes around. And that's one way we can find a planet. The other way is really easy to understand, much easier than any gravity-moving planets. The other one's just exactly how an eclipse works. So sometimes we're very lucky on Earth when the moon moves in front of the sun, it actually blocks the starlight. Well, a planet can do the exact same thing. Now, the effect is much smaller. What I'm showing you here is kind of a simulation. You see the planet darts in front of the sun. That's that black dot you see there. And it just blocks a little bit of the light. Now, it took a long time for this method to come very good because obviously a planet's very, very, very small compared to a star. Like the Earth is millions and millions of times smaller than our sun. And so it only blocks a tiny bit of light, not like the moon, which blocks all of it because it's so close. And so this is another way of identifying planets out there. And so we live, as I was saying earlier, in this amazing time period where I wouldn't call it easy to find planets around other stars, but it's become standard. And what I'm showing you here on this plot on this slide is all the different stellar systems we've found and superimposed on the solar system. So in the dashed lines you see here are our solar system. Obviously, the closest planet here is Mercury, and then it goes Venus, Earth, Mars, and then the big one outside's Jupiter. You might notice all these other different stellar systems, the sun obviously being, or a star being at the center. Some are really weird. You got really small, quick moving planets close by, and then one really big one further away. And you've got everything you can imagine. We're really seeing imagery right now. So in terms of finding planets, we're sitting golden. We're sitting real comfortably in terms of being able to, if you say to me, hey, Joe, there's a star. Can you tell me if there's a planet around there? I now have the technology to do that. So as I was mentioning earlier, now the question becomes, is there possible for life to exist on these planets? And this is very important to us as a species as well, because just recently, within the past few years, we've actually identified a planet around our closest neighbor. And our closest stellar neighbor. So obviously the sun is a star, and our closest stellar neighbor is a star called Proxima. It's about 4 light years away. To remind you what a light year is, that's about how long light takes to travel in a year. It's very far away. But in terms of the galaxy's term, this is our next door neighbor. This is a person who gets your packages delivered to you when you're not home, in stellar terms, if I did a Dutch translation. And so it's very interesting to know that we have right next door to us a star that's hosting a planet. And we also know this planet exists in what we call the habitable zone, or if we want to use a more public phrase, a Goldilocks zone. This means it's neither too hot, neither too cold to have liquid water on its surface. And this is really important because as far as we know, if we take a very basic definition of life, water is the most important essence to making sure life can exist on the surface of a planet. And so this is kind of a visualization of that Goldilocks zone I told you. So the sun's at the center. Obviously, these aren't the scale. This is just to help us visualize. And then we've got Mercury, far too hot, much too close to have water on the surface. Venus, still too hot on the outside surface, barring like all the complications of its problematic atmosphere. Venus is the hell in the solar system, so you definitely don't want to go there anytime soon. And Mars is on the edge of what we call this beautiful zone that the Earth sits right in the middle of. You might, if you're a philosopher, you might find this a very convenient definition, right? Because, hey, look, Earth's right in the center. Earth being at the center of things never boded well for discovering new things. That's something to keep in mind. Again, happy to have conversations about different definitions of how to find life later on as well, if you think that's interesting. But there's a big discovery. Remember I mentioned Proxima. Now, Proxima, our nearest neighbor, isn't quite a star like our sun. It's much smaller. It's about only about 10% the size of our sun. And so what does that mean? Well, you can kind of visualize. If I shrink the sun, that means it puts out less energy. So if it puts out less energy, to make sure we don't have, say, ice all over the Earth, we actually have to be closer. And so this is what we see for kind of an equivalent system. This is called a trappist system for people that are playing at home or familiar with this kind of stuff, a very famous system nearby, and it's an M dwarf. So this red dwarf at the center, very similar to Proxima. And you can see what I'm trying to show here in this graph is that now the habitable zone is significantly closer to the star. So instead of being far out where Earth is, this is within all these planets, or within the orbit of Mercury, which is quite amazing to think that's how close you have to be. So this has very important implications for understanding whether life could exist here, because this Goldilocks zone, this conventional habitable zone I've been talking about, is defined in just a very easy sense. Is there liquid water on the surface? But we know there's a lot more important things that we have to answer whether life could exist on a planet that are just independent of how close the planet is to its star. And the classic one is what Ciara talked about. We know our star isn't static. It just doesn't sit there plodding along perfectly in the sky. It does seem like on our everyday life that's the case. But when we look in radio and UV and other wavelengths, our star undergoes these massive explosions, these coronal mass ejections, and Ciara showed some of her in her talks. And these have huge implications for whether life could exist on the surface. When, as Ciara said, when this hits Earth, this has massive repercussions for satellite communications, all kinds of stuff. And as I'll explain in a second, we're very lucky here on Earth to have a few important features that protect us from such things. But remember, I talked about this M dwarf, Proxima, being all these planets are so much closer. When this eruption happens, likely we're very far away from the sun. So one, by the time it reaches us, it's not so bad. And number two, we travel such a big area, so the chances of these hitting us is much lower because we're further away. For these planets around like Proxima, this is a much bigger issue. We don't understand how much this impacts them. Even if they're sitting in this nice Goldilocks zone, could they have life if they keep getting hit by these massive explosions from their star? And as Ciara alluded to, but also as I just mentioned before, we're very lucky here on Earth that we have a magnetic field. So the white lines you see here are our magnetic fields, and this red thing that comes barreling and hitting our Earth is at one of these coronal mass ejections. And so what's happening here is our magnetic field, we understand, is very important to maintaining our atmosphere. Because we didn't have our magnetic field, these coronal mass ejections could come in, and stellar flares, all types of radiation could come and just strip us of our atmosphere, and we become a barren rock just like Mars. Mars doesn't have anywhere near the magnetic field strength we have. And so as we understand Earth, not only do you need to exist in this habitable zone, but you need a nice star like our sun, not a crazy star, and also two, that's always exploding. And number two is we need a good magnetic field. Now, when we find all these planets using the optical methods I mentioned, the transit method and the radial velocity method, we have no idea what the magnetic field properties or what the star's doing through those methods. And so this is where radio comes in. Now, luckily, again, Ciara, sorry, I'm just going to take a break. Ciara mentioned this earlier. Usually when we talk about light, in everyday terminology, we think about turning on a light. But to an astronomer, light means a lot different. It means what you've probably all heard of before, the electromagnetic spectrum. So to an astronomer, light comes in many different flavors. And luckily, Ciara told us all about them. So we got X-rays, ultraviolet. So these are high energy. They trace energetic environments, visible, infrared, microwave, and radio, and they just communicate essentially the energy of the light. And the one where I specialize, as Ciara did, is in the radio. And this tells us particularly about magnetic fields, kind of thinking about like your bar magnet at high school. So this is now where I try to do a live demo. And this all could just completely fall apart, but I will try my best. So what we're going to do now is we're going to try and play a quick quiz. Just a little bit of fun because you're probably all zoning out by this point of me talking. And it's going to be on this, just a web browser. All you need to do is do kahoot.it and then, so 3810024. Maybe, well, I'll give people another 30 seconds to join, but I also thought I would read fun facts just to make sure people don't get bored. One of them is clouds at the center of the Milky Way smell of rum, taste of raspberries, and are packed with booze. So these have these giant molecular clouds in the center of the galaxy, which are, are actually full of ethanol and have these kind of really fragrant colors, which is kind of amazing. But these are spread over large areas. So I don't think you can smell it very easily. Okay, I think now we'll get underway. We've got about 30 people. Thanks everyone for joining. Let's get underway. It's Astronomy on Tap quiz. And 3, 2, 1. So what is the brightest object in the sky at optical wavelengths? So optical wavelengths are the same wavelength as what you use your eyes with. And so the options are the International Space Station, it's very close, Venus, right? Jupiter, or the sun. So while you answer that, you've got some time. I thought I'll tell you some random space quizzes. So a really interesting one I like is about Mercury. So Mercury is, the closest planet to the sun. On Mercury, a day lasts nearly twice as long as a year. So a year on Mercury is about 88 days. So that's what it takes around to go there in the sun. But a Mercury day, because it rotates so slowly, is 59 Earth days. So that is, so more or less you're only 2 days old. I mean, by the time you're 2 days old, you're actually 2 years old. And so it kind of gives an interesting concept of how we define time and also time and everything else like that. Oh, well, everyone's very smart. I'm glad. Congratulations. 24 people got correctly guessed. The sun is the brightest object in the sky at optical wavelengths. I'm glad because you shouldn't go out like Ciara said and look at it with your eyes. And you get a little bit of points for answering really quickly, but I think that's unfair because obviously there's lag. So we'll just ignore the point system. What is the brightest object in the sky? X-rays. So rather than optical wavelengths, so we have other stuff like the Vela pulsar. A pulsar is the remnant of a massive star. At the end of its life, it undergoes a big explosion, and what's left over is really dense. Like if I could hold a teaspoon of a neutron star or a pulsar, it would weigh as much as the Earth, which is, wow, that's pretty crazy. And then you got Cygnus X1, a really bright X-ray binary. This is where a star is next to a black hole, and it can donate material onto the black hole. And then you have the sun again. And then you have Alpha Centauri, which I've actually misspelt, which is really shows I'm paying very close attention to how to follow this. Let's just continue on. We're getting answers in, which is good. 10 seconds. All right, let's do last 3 seconds. Oh, a bit more split, but it's in fact the sun again. Well done to the people that got that correct. It was a little bit tricky. Cygnus X1 is incredibly bright in the X-rays, but not as bright as the sun. And we've had some change. Hello is still winning. What is the brightest object in the sky on UV? So what I'm showing you here is actually a really fascinating time period, and shows that humanity can work together to solve a climate crisis. So on the right here, I'm showing you our ozone layer and the hole over the Antarctic in 1988 when we still had CFCs. And on the left, I'm showing it as today, and that's because we got control of that. So remember, just ask the brightest object in the sky on UV. Is it the moon? Is it Jupiter? If it's Alpha Centauri, which is Alpha Centauri, I had a couple. Clearly, I couldn't spell Centauri. Something's gone very wild there. And we've got the sun. So yeah, just to finish on here, this is huge progress, and as humanity, we have something to be proud of. As a global citizen body to solve such a pressing problem as that, and hopefully we can solve the other ones in a similar vein. All right, last couple seconds. What is the brightest object in the sky in the UV? It is in fact the sun. Everyone got that one right. Well done. Maybe the correlation with UV and burning. Jupiter was not the right answer. Sorry to the person who got that wrong. Okay, now this is the last one. What is the brightest object in the sky in the radio? So this is just a picture of the Westerbork here. This is a famous radio telescope out in the Netherlands. We've already talked about LOFAR. I'll talk about LOFAR again, but this is something we can only have LOFAR because we built on the tradition and the privilege that Westerbork gave us. So what is the brightest object in the sky in the radio? We have the sun again, Vela Pulsar again, Jupiter again, and Cygnus A, a radio galaxy. So you heard about that again also with a few people where you have material falling into a black hole and you get these big jets. That's one of these is Cygnus A. You guys were already doing a quiz on that earlier. Wonder what you're going to get. All right, let's see. We got a couple of questions. This is a trick question because, everyone's answered. Most people got it right. Well done, 15 people. Usually most people don't expect that. So to recap here, the sun is the brightest object in the sky at every wavelength, pretty much. So X-rays, UV, radio, all that's, X-ray, UV, infrared, microwaves, all those other things. The only exception to this rule is Jupiter at radio frequencies. And that's important because discover the planets. And so this is what we're going to do now. All right. So what I was saying before is the brightest object in the sky is in fact Jupiter. So there's a very simple thought experiment you can do is, could we see a Jupiter around another star system? And the answer is, well, we probably should. If it's the brightest object in the sky, if we've got a sensitive enough instrument, we should be able to do that. And that sensitive enough instrument is this LOFAR telescope you see here, built and housed in the middle of the Netherlands with stations all over Europe, including one in Ireland, as we heard earlier. And this allows us to go really sensitive at low frequencies. So frequencies at which you essentially turn on your car radio. When you hop in your radio to drive down, the A28 or one of the highways in the Netherlands, you turn it on and you hear your radio. I'm trying to look at the universe at that frequency. And so probably not ideal to build a telescope in the middle of the Netherlands, but we're lucky we're low, so we're kind of avoiding radio stations. But anyway, that's a long story why it was built here. But we're very lucky to have so many antennas on the ground that allows us to find Jupiters elsewhere. And so how do we find Jupiter? Why is Jupiter so bright at these low frequencies? And the reason's got to do with aurorae. Now, you probably think of aurorae as these beautiful lights you see out in when you go to, say, Norway or Iceland or the Arctic, if you're lucky, or the very tip of Canada and Greenland. These are incredible. And if you're from the Southern Hemisphere, I am a Southern Hemisphere person. I shouldn't show Northern Hemisphere bias. So Antarctica, South Chile, if you're very lucky, the edge of Tasmania and New Zealand. And that's Aurora Australis, which is just the same as the Northern Lights. You get them because what happens is the sun, when it emits these big ejections, can interact with our magnetic field and cause these aurorae at the poles. If you've ever gone hunting, you want the sun. If you've ever gone hunting for these lights, you want the sun to be active so you can see these things. But the radio, they're very, very bright. And in Jupiter, the reason for this hasn't got to do with the sun like it does on Earth. It's actually got to do with the fact nearby, just by luck, there's a very active moon called Io or Io. Now, this is one of the moons that Galileo discovered. And it just happens, if you remember high school physics, what happens is it's a conductor. So what's happening is it's orbiting Jupiter, and Jupiter has a magnetic field just like the Earth. And as it orbits Jupiter, it sets up a current which drives particles down to the poles of Jupiter. Just like when the sun causes an explosion, hits the Earth, these particles go to the poles because that's where the magnetic fields funnel them. And it's just like a big funnel that drags them down to the poles. And this is where you get the aurorae. For Io, it's doing the same thing, but it just does it by itself because it's a conductor. This is equivalent to a magnetic, like a metal bar in a magnetic field when you did high school experiments. It's called an electro. It's the same thing for Dutch people. When you ride a bike and you've heard of a dynamo, this is pretty much the same premise. You're making a conductor move in a magnetic field, and this can drive electrical currents. And this drives these beautiful aurorae we can simulate here. See, this is a picture of some of the aurorae we can make out. And you see this dot with this long tail. That's in fact Io being the brightest there. And these make these beautiful aurorae. I've had my picture behind me, and these are some of the ones you can get from Iceland. So that is incredibly bright in the radio, and it tells us all types of things. It tells us about the magnetic field strength of the planet, which we can't get at any other wavelength. So if we find a planet around another star that's sitting in our Goldilocks zone, we can use LOFAR to say, has it got, say, a magnetic field similar to Earth? If it does, then maybe it could maintain an atmosphere in the face of all the activity from its star. If it doesn't, if we say, hey, look, it has no magnetic field, that makes life much harder to evolve as we know it. Again, I've already given you lots of caveats about life. And so what does it look like trying to find one of these things? Well, this is a radio image. Doesn't look like much. You can kind of see fluff hanging around. That's problems with our telescope. Well, Wendy, who's an expert at this, will go, well, that's not problems. You know, this is amazing. But what I'm saying is that this is where this is just some smudges. You know, you probably think of optical telescopes. You see spikes hanging off stars. This is kind of the radio equivalent of seeing spikes hanging off stars. And how do we find a star? Well, we already know that, I should have told you earlier, most objects in the sky, even if you see these dots, if I make your eyes radio antennas for one day and told you to look at the sky, most dots you see are in fact galaxies very far away, material falling into black holes. That's what's really bright at radio wavelengths. But we've been using LOFAR, and we found our very first star that we didn't expect to find. And this star, we think, is exactly what we expect to find when a planet's orbiting it. And it's similar to the Jupiter and Io system. But instead of just Io, what you have is a planet. And instead of Jupiter, you have a star. And this can drive those aurorae and be really bright. And so maybe my takeaway, just to finish up, and I'm sorry if I went over a little bit, is that we're really at a really interesting turning point for astronomy when it comes to understanding life out there and planets out there. And with radio astronomy, we're at the cusp of saying, can we find planets in the radio? And what does that tell us that we can't find out at other wavelengths, particular magnetic field strengths, and tell us all about what that star, its host, is doing. When it explodes, like Ciara showed, we can trace that and understand that. And is that more energetic, less energetic than the sun? And yeah, these are first baby steps. And I think there's lots of simple ideas here, but over the next decades, we'll see lots of growth. And thank you for your patience and joining in. And hopefully you had a bit of fun, and feel free to ask me any questions. And I'll stop there. Thanks.
Thank you, Joe, for this excellent talk. And it was super interesting to go through it. And also the game and everything was very, very engaging. I hope our audience also really enjoyed it. And we still don't have any question. I think it's also partially because it was super engaging for everyone. But while we are waiting for them, I have a question myself that when during the quiz, there was this thing that, okay, Jupiter is brightest in radio. But is this what we see in all throughout the radio wavelengths? Because it spans like a big chunk, or if there is like a cutoff?
Well, good question, Lamin. So the spectrum, so how the light emerges from Jupiter does vary. So you're correct. Is it the brightest in the radio at all frequencies? The answer is no. It's only at the lowest frequency, which LOFAR is sensitive to. So technically, your answer could be the sun as well. So for example, if you use Westerbork, or use like the very large array in America or the compact array in Australia, the sun will be brighter than Jupiter. But with telescopes like LOFAR, Jupiter is the brightest. So I should say really long radio wavelengths or very short radio wavelengths. But yes, you're correct. That's the way it goes.
Yeah. Thank you. And yeah, I think Wendy wants to ask a question.
Yeah, I could ask a question there, Joe. So the planets we can detect right now, are these only around more active stars than our sun, and with yeah,
that's a good question.
Stronger magnetic fields than, say, the Earth?
Yeah. So right now, there's a lot of effort going into finding planets around dwarfs, these small red dwarfs, are much smaller than our sun, 10% the size of our sun. The reason for that is because the habitable zone is much closer. So that means you need to look a shorter amount of time to find something in this conventional habitable zone. Remember, imagine you're an alien and you're looking at Earth, right? You're very far away and you're looking for a transit. You're waiting for the day Earth passes its sun, our sun, and then goes around and does it again and does it again. To be confident that you've detected a planet like that, you need to wait 3 years, right? It takes 3 years for the Earth to go around the sun. So you need to wait 3 whole years to do that, to find an Earth twin around a star like our sun. Humans, we don't have the patience of that. We want the answers now. And so the answers are, well, we can go to these smaller stars, and guess what? The habitable zone is much closer, as I showed, right? It's shrunk. And so they only take a few days to do that. So you only need to look for like 10 days, and then you can answer the same question: is it at the right distance? And so there's a lot of effort going into finding around these red dwarfs, which are much more magnetically active. But the problem there, as you alluded to, these M dwarfs are much more active than our sun. You know, we see that eruption Ciara showed with these CMEs. We think they happen more regularly, and it's much more complex. So maybe life can't exist around these stars at all. But hey, look, this is a fun part of being an astronomer, as you know, Wendy. You know, there's lots of unknowns, and why not have fun and try and explore them? If we don't know the answer, someone has to find out first. Right?
Thank you.
Okay,
We have one more question. It's from Roger I in the YouTube chat. He asked, "Are we observing Proxima b for long periods of time using Event Horizon Telescope?"
Yeah. So good question, Roger. So a lot of people, it's our closest star. So everyone looks at this. We're doing it at all types of wavelengths. So everyone's staring at this close star. The question you asked with the Event Horizon Telescope is a good one, because the Event Horizon Telescope is essentially it's up. I don't know if it's slightly better. Anyway, the preface is it's the highest resolution instrument we have, or one of them, on Earth, right? We can resolve things really far away, which you're familiar with, that beautiful black hole image. But the problem with doing it for Proxima is it's only bright at low frequencies. This is kind of a question that Wendy asked. And so the AHT works way too high frequencies. And so we just won't ever see that the aurora that I mentioned before, it cuts off. It runs out of energy. So that we'll never see it in that way. But the problem with Proxima, ironically, is it's in the southern hemisphere. So telescopes like LOFAR can't see it, which is really annoying. I'd love to look at Proxima with LOFAR, but unfortunately Earth gets in the way. I only can point my telescope so far to the ground before I hit the ground. And that's what's happening with Proxima. There's instruments in Australia, but it's not quite LOFAR. But SKA, that will be a big game changer with this understanding. People are looking and they're like, oh, maybe there's something there, but it's really hard to do it without like a LOFAR equivalent in the south, in the southern hemisphere. So ask again in 10 years, hopefully I have a better and different answer.
Great, thank you. And we don't have any more questions now, but then there is a few, a round of applause from the audience that they really enjoyed it. And especially I'd like to read the comment from Fred that he said, this was a very entertaining and informative presentation, and I would have liked to have more instructors like you. So,
well, thank you, Fred. I appreciate the feedback.
Yeah, so with that, I'd like to thank you once again, Joe, for this really entertaining and engaging talk. And I think we'll move on with the answers of the games with Stella.
Yep. Thanks, guys. Thanks for hosting.
So the answers of the games, when we start with the first one. So the radio telescopes and where they are located. So the first one is the Meerkat telescope located in South Africa. The second one is the MWA in Australia. The third one is the LOFAR telescope in Netherlands. And the fourth one is ALMA in Chile. The second one, with these telescopes, you could theoretically be able to read a newspaper standing in blank. So we find that with the Event Horizon Telescope, you could be reading a newspaper in New York while standing in Berlin. And with the Atacama Large Millimeter Array, you could read a newspaper in New York while standing in Los Angeles. So the longest baseline for these telescopes. For the first one, which is the Meerkat telescope again, it's 8 kilometers. For second one, the JBLA, is 36 kilometers. The VLBA is 8.6, and ALMA is 16. So what wavelength is this image of our Milky Way? First image is of the X-rays. Second is infrared. Third is radio, and the final one is optical. Now, which of these discoveries were made in which year? The first pulsar was discovered in 1967. So a pulsar is a fast-spinning neutron star that emits periodic pulses of radiation. And the first pulsar was detected by Jocelyn Bell in 1967. And fun fact for it, they originally nicknamed the pulsar LGM-1 for Little Green Men, as its origin was at the time uncertain. Number two, the first exoplanet. So the first confirmed detection of an exoplanet was actually through observations of a pulsar in radio wavelength. The researchers found strange patterns in the pulses from a pulsar and determined that the pulsar must be orbited by at least 2 exoplanets, and this happened in 1992. The first exoplanet that was detected around a sun-like star was 3 years after this event. So 3, the direct image of a black hole, it's 2019 with the Event Horizon Telescope. And finally, detection of neutral hydrogen was in 1951. So this entails the detection of the 21 centimeter line, which is in the radio band. And it's caused by a flip of the electron spin within the neutral hydrogen atom. So when the electron spin flips, the energy state of the atom changes and it radiates in this 21 centimeter line. So although the existence of this line was already predicted by Dutch astronomers before, it was first actually detected in 1951 by astronomers at Harvard. And finally, game 2. So the first host was supergiant elliptical galaxy. The second one was a lenticular galaxy. And the third one, I have this thing moving away. It's the merging galaxies that you see in the center here. So this image already had actually the visible and radio mixed, so that's why we had to block the center. Now, fourth one, and it's the spiral galaxy. It's a spiral galaxy, not the spiral galaxy. And fifth, it's a group of galaxies. And the final one, we have a supergiant elliptical galaxy again for this host. The tiebreaker, so how many stations will the telescope, will the SKA telescope consist? And the answer is 709 stations. And finally, we have 2 winners as always. The non-astronomer winner is Wim Noble with 19 out of 24 points. And the astronomer winner is Sarah and Alma with 20 out of 24 points. So congratulations to the winners. We will contact you through your emails that you provided us and send you a little present for you. Thanks from me, and back to Wendy.
Great, thanks, Stella. And thanks to our games team for putting together tonight's games as usual. So once again, thank you to everybody involved. Thanks for joining us. It's been great having you. I've seen people in the chat coming from all over the world, from the US, India, South Africa, across the channel in the UK, Dublin, also local people from Leiden and Amsterdam. It's great to have you. Thanks for tuning in. It's always a pleasure to do this for you. If you're interested in more such events, have a look at astronomyontap.org. All of the Astronomy on Taps around the world advertise their events, and most of them are online at the moment. A very big thank you to our speakers. We're sorry that we can't give you these in person and offer you a drink in the bar, but we will get to you a Astronomy on Tap pint glass, or is this a schooner glass? I don't know. So thank you very much for your very, very good talks tonight. It was very interesting. And finally, a big thank you to everybody in our team. It's a big effort by a number of people to put on these events, and we appreciate all of you. So thank you very much. Hope you have a good night. And I seem to have lost the slide. Yes, our next event will be on the 22nd of February. So see you in a month's time. Great. Good night, everybody.
Thanks, Wendy, and everyone. Bye-bye.